Context VAE is a novel approach of trajectory prediction for ego vehicles. It uses an architecture of Timewise VAE as the backbone and employs a dual attention mechanism to encode the context of semantic map and agent states simultaneously in a unified manner for trajectory prediction. The overall architecture of Context VAE is light-weighted and can support real-time inference. We experimentally show that Context VAE is able to achieve high-quality predictions with real-time performance on multiple large-scale datasets. The basic architecture of Context VAE is a variational autoencoder. However, instead of using a certain latent vector for prediction at all time steps, we introduce Timewisely generated latents, for the sake of better capturing the highly dynamic nature of human decision-making during driving. The final output of Context VAE is a distribution of trajectories represented as a series of displacements. To capture the movement patterns of the vehicle agent under prediction, Context VAE takes the map information as the environmental context and agent states as the social context, and uses the encoded context as the condition for latent generation. This results in a conditional, Timewise VAE architecture as the backbone of Context VAE. Beyond that, Context VAE performs posterior approximation backward. Such a structure makes the encoder always take into account the whole trajectory, including both the future and historical segments, when performing encoding at each time step during learning. Our context encoder is composed of two components. A map encoder encodes the semantic map information. A state encoder relies on a social attention mechanism to extract the movement pattern of the vehicle under prediction from the observable social features exhibited by vehicles on the scene. Previous works perform map encoding and state encoding typically in a separate VAE. The two encoded results are processed independently and put together as the context condition. In Context VAE, we propose a unified scheme to perform context encoding, where the environmental context reflected by the map information is used as a contextual condition for state encoding. By doing so, the state encoder can take into account the environmental influence while encoding the agent state features. To better capture the map features for state encoding, we propose a map attention mechanism that uses the extracted map features to initialize the RNN encoder for agent state encoding. This results in a dual attention mechanism in our approach. During training, Context VAE is optimized to minimize the evidence lower bound Timewisely. In our implementation, we use Gaussian distributions to model both the prior and posterior and the distribution of position displacement at each time step. When performing prediction, we draw latents from the prior only. The ground truth trajectories for posterior approximation are not required anymore. To demonstrate the performance of Context VAE, we run tests on three large-scale datasets, NewSens, Lyft and Waymo. As we can see, Context VAE achieves lower prediction errors in all the three tested datasets. Here, we show some prediction results of Context VAE on the dataset of NewSens. The blue line denotes the observed trajectory of the target vehicle under prediction. The red line denotes the ground truth future trajectory that the target vehicle takes. The orange lines on the left plot are the predicted top 5 most likely trajectories. The right plot shows the predicted trajectory distribution heat map, which are generated using 2000 predictions. The other colored dots denote the neighbor vehicles. Here are some results from the Lyft dataset. As we can see, while taking into account the neighbor vehicles when doing prediction, Context VAE also can generate map-compliant trajectories accurately capturing the target vehicle's movement intention. Here, we show Context VAE can generate multimodal predictions to capture the multiple possible lanes that the target vehicle could go. Here, Context VAE generates social-aware trajectories taking into account neighbors distributed around the target vehicle. Here, we show some results from the dataset of Waymo. We can see that besides generating map-compliant predictions, Context VAE also can work for vehicles driving off-road. From those results, we can see that Context VAE is a fully context-aware approach. It is able to generate map-compliant, multimodal predictions while also taking into account the social features exhibited by neighbor vehicles. In this slide, we highlight the real-time performance of Context VAE during inference. As we can see, Context VAE is not sensitive to the map encoding module. When employing a small module for map encoding, Context VAE can run at around 30 fps, while keeping low prediction errors consistently. In summary, we propose Context VAE as a novel approach for context-aware vehicle trajectory prediction taking into account both the environment context of map information and the social context of neighbor vehicles on the scene. We show that Context VAE can serve as a strong baseline for vehicle trajectory prediction tasks with real-time inference performance. We refer to our paper and project webpage for more technical details and results of Context VAE.